So this is intended to be a recorded version of the talk I gave at CSME 2026 at Vancouver, Canada this year. Hi everyone, my name is Howard. I'm from the University of Toronto, and today I'm going to talk a little bit about applying active flow control on a circular cylinder. So, starting with a bit of background motivation, the underlying physics that I'm trying to combat is flow separation. That happens when there's an adverse pressure gradient over a surface. Now, when there are excessive flow separation on an airfoil, that can lead to stalling, which is quite not ideal as we lose a lot of the lift generated by the airfoil. To get around this, one of the things that we can do is apply something called active flow control devices. Here's some smoke visualization from one of the lab's alumni. So on the lower left, without control, where the red arrow is pointed now, the void region is actually a recirculation. So this is suggesting that the flow is fully separated and therefore is fully stalled. Now on the right, with adequate control, we can see that the streamlines are a lot closer to the flow surface and the wake size is a lot smaller as well, especially in height. And this suggests that we have kind of prevent or altogether suppressed the stalling, recovering a lot of the lift back. Now, one of these active flow control devices is something called Synthetic Jet Actuators, SJA. They really come in all forms or all shapes and sizes. This is just one of the ones that my colleagues actually use in the wind tunnel. And they're very lightweight nowadays. This only weighs 16 grams. So a lot of potential applications on, say, small to medium UAV especially. Now, the way these SJAs works, they're kind of like similar to your human lungs. There's a diaphragm inside a cavity, and during the ingestion cycle, the cavity volume expands and it kind of draws the air in. And then during the expulsion cycle, it kind of squeezes it back out. And here's a little visualization of how it looks in a quiescent environment. The alternation of the diaphragm can result in this kind of vortex ring formation. Kind of looks like mini donuts. Now, the geometry that I've chosen to apply the active flow control on is a 2D circular cylinder. It's quite often called 2D because the geometry itself is 2D and the flow is nominally two-dimensional, but the simulation itself is 3D. The software of choice is OpenFOAM. The model is well and it's a well-resolved LES. Um, cylinder diameter base Reynolds number is 3900. This is in something called the subcritical region, where the separation actually happens at laminar, as indicated on the right, where the red arrow is pointing. But then the shear layer then transitions into turbulent. And if we look at the wick, the structure is highly three-dimensional. So it's another reason why this has to be done as a 3D simulation. In terms of the boundary condition, it's just a fixed inlet, laminar inlet. And to create the 2D infinite span-like geometry, I'm applying a periodic boundary condition for the front and back. This would be equivalent as a side of the wind tunnel. And for any formers out there, I'm using cyclic AMI to be specific. Validation was quite thorough, primarily done with PIV results. I'm only showing Ux, U prime, U prime here, but I also compare Uy, U prime, V prime, V prime, V prime, just to make sure that higher order statistics are also agreeing with the experimental data. Uh, and here the SG included case is basically with the nozzles built in, but not turned on, and it doesn't change the flow significantly. Now, just to make sure I didn't get lucky in the wake, I also validated it in terms of finding different results and making sure that the tap pressure tap also aligns well with experiments. This kind of gave me us a lot of confidence to make sure that both the wick and new wall flow are accurate. Finally, two variables I want to highlight. First is the drag coefficient of 0.97, and then the second is a show hole number of 0.21. Both are well within range of the existing literature. Now, moving to the more exciting aspect of this talk is the air rate of the actual actuated case. So I'm applying 5 circular nozzle SJAs onto the circular cylinder at a theta equals 90. So basically the jets are perpendicular to the free stream velocity. And here on the right, we have like the red regions, what I'm identifying as the actuator region, where it's control. So later on, when I do force calculation, it's only based on the red region surface, but the gray zones are still simulated. The mesh is primarily a slightly modified O-grid, 10 million cells, the maximum Y plus of 1.4, and a maximum Z plus of 25. I am resolving at least 89% of the turbulence in the entire flow domain, and there's a maximum eddy viscosity to kinematic viscosity ratio of 1. That is usually located around the exit and outlet or near the exit. Near the actuator zone, especially mid-span, that's usually around 0.3 to 0.4. Now, if we zoom in lower at the actuator region, so again, I am applying 5 circular nozzle SJAs. Now here I haven't modeled the diaphragm and the cavity of the SJA in order to reduce cost, and instead I'm applying a analytical boundary condition onto the velocity. And this is kind of how the actual boundary condition looks like in the y direction. That's the UY. And I must say this is a very elegant solution, and it reduces the cost quite significantly compared to a dynamic mesh approach. Couple SJA parameters I do want to highlight. First of all, the ratio of the diameter of the cylinder to the diameter of the jet is 25 to 1. The SJA is modulated at a frequency of 6 Hz. This comes out to a reduced frequency f plus of 1. Now the f plus is chosen because it seems to be quite promising, quite promising as a starting point for full control, not just on the cylinder, but also in backward-facing step and airfoils. And then finally, to go with the modulated frequency, I'm giving it a duty cycle DC of 50%. Now, the modulation envelope or the signal actually looks something like this. Instead of just a standard step input, I'm using a blend of the step input, but then at the start and the end of each burst cycle, I tapered it off with a sine wave. This is primarily done to combat numerical instability. During preliminary computation, when I just use a step input, it kind of created a lot of issues for the pressure software. It had to work really hard and the results weren't that good. So this kind of eases the software and kind of warms it up. So starting the results section with some time average streamlines. On the upper right, we have the baseline case, not overly exciting. Just have 2 primary recirculation bubble. And the profile are symmetric, which makes sense. The geometry itself is symmetric. Now, on the actuated case, and these are taken at mid-span, we can see that even though we only have 5 SJAs and at a pretty modest blowing ratio of 0.84, it changes the recirculation zone quite a lot. We never expected it to suppress separation outright in this configuration since we're only actuating one side. But we can see that on the upper surface, it's almost like the SJAs are actually trying to reduce the separation bubbles length and causing this quite asymmetry in the recirculation zone. Now, if I look at the boundary layer profile, here the black line is the baseline and then red dash are the actuated. We can see that upstream or left of the SJ exit, the boundary layer profile of the 2 cases are identical as expected. But from the jet exit onward, it kind of changes the boundary layer profile quite a lot. And if I zoom in, we can see that right at the jet exit, there's a near wall increase of near wall momentum. And in some of my past work, I've seen this on a flat plate. Here, the effect is a lot more significant. It is actually delaying separation by at least 45 degrees on the upper surface, and quite remarkable for the strength of the jet. Now, from this, I'm getting a lift coefficient of from 0 to 0.1. It also came with a very marginal increase of drag coefficient. Now, moving on to some turbulence variables. So I have some time average TKE contours here. This is primarily to show where the probe's locations are, meaning that probe 1 is in a shale layer and probe 5 is kind of all the way into the wake. Now, here are some turbulence kinetic energy spectrum. The horizontal axes or the frequencies are normalized by the wick frequency. This is basically the baseline wick shedding frequency. Now, on the baseline case, we just have a single peak at unity, which makes sense. That's why I normalized it with. Now, on the actuated flow, the same probe in the shale layer probe 1 actually had a lower energy at the same peak. And we can see that the same probe, there's a lot more spikes at the higher frequency range. Now, if I take the probe 1 out, again, this one in the shale layer, and it shows the most difference compared to the baseline case. And this time on the lower left, I'm plotting V prime, V prime instead of U prime, U prime. And we can see that the changes is quite significant. In the baseline case, don't really think it was really turbulent. It kind of looked transitional. But in the actuated case, I think what the SJA did was that it functioned as a turbulator. And it kind of triggered a premature transition to turbulence. Now, a couple major spikes. So the burst modulated frequency is the highest peak. And then the last one, it might be manifesting low. I think that's actually the base SJA frequency, the modulated one. So it kind of survived all the way down there. Now, wrapping up the results section with some Q criterion contours animations. Here's an isometric view of the computational domain. Now it's a little small, so I also have a zoomed in view. And what I've also done is that I've kind of trimmed off the non-actuated zone. So this is kind of like the red region from a couple of slides ago where I'm only showing that section. And what we can kind of see is that the SJA comes out almost like discrete SJAs. We can almost count there's 4 rows and each row has 5 SJA, but they kind of clump into a larger eddy shortly after in the shell layer. And here's a side view, and it kind of tells a similar story where it comes out, the vortex ring grows low in size, but then it just forms a larger eddy. And this is a isometric view and time average. I kind of trim off some of the span-wide section just so we can zoom in a little bit more. And overall, what I can see is that it's a cumulative effect where we're getting the best performance at the middle of the array. And then the first and last jet actually had the structure that almost looks like a barrier. And this kind of reminds me of the Moses splitting off the ocean with a lower trench in the middle. Now, in terms of future work, I think the most immediate would be span-wise control authority. And a bit of a spoiler, having more SJAs, their cumulative effect really does actually enhances it. But it's gonna need quite a bit longer to run to get some time average results. Then from there onward, I think an F plus analysis or different running the case at different F plus would be promising. Some of the existing literature suggests that F plus of 4 and F plus of 10 to also be worthwhile for a cylinder. Then some spectral analysis, especially with SPOD for the case in higher frequency, would definitely help to see what's happening in the flow. And then finally, if I ever discover the fountain of youth, there will be signs, and one of them would be me trying to apply the SJA's array onto a NACA airfoil and maybe even modeling the entire wind tunnel. But quite costly, so someday. Now, before I wrapped up the presentation, I want to take a few seconds to thank you MDPI Fluids for their generosity in sponsoring part of my travel. This really helps a lot for PhDs and or earlier researchers like myself to get more exposure of my work. And any of the viewers that are doing their PhD or in their early stages of a postdoc, you are eligible to apply, and I strongly recommend you to do that. And I've included a link in the description of this video. And well, thank you for listening.